we'll proceed on the algebraic side of the calculus. So we have seen the parametric vector side of the calculus. So the tough part anyway we have taken care. That is the parametric vector side of the calculus. Now we would tackle the uh, calculus part, the algebraic part of the calculus. So parametric vector is important when we are too much particular or serious about the direction. So then means if I have to have the direction at each point, then we go for the parametric vector. Otherwise, the traditional way of handling the calculus is algebraic equation. So what is gradient vector? That we calculate through algebra. So that we will see. So that is the concept, that kind of dealing with the algebra and then dealing with the kind of calculus. So if we are particular about the direction, then if I have parametric equation, parametric vector, then position vector, the displacement or the equivalent, that equivalent of the position, equivalent of the parametric vector is algebraic equation, where algebraic equation does not signify the direction at each point. If I take point by point, then what is the direction at that point, that can be only signified by the parametric vector, whereas algebraic equation is not capable of that much. Beyond that, if I go for velocity vector, acceleration vector, I mean the what's first derivative, second derivative, and integration and those kind of things, still we want to have the kind of direction vector. Okay, so we want whatever the algebraic equation we have, as per the algebraic equation we have parametric vector. We also call it parameterization into the vector. So if I have a curve and curve is algebraic equation, then if I say that I am doing parameterization, means I am converting this algebraic equation of the curve into parametric vector. Parametric vector, immediately at each point in the curve I have a vector. Okay, so in calculus, where we have calculation for infinitesimally small distances, there at each point if we have separate vector, and then we have algebraic equation for the vector at each separate point, then parametric vector considered as more accurate from the algebraic vector. So if I have a curve equation, and curve equation, if I am able to transform it to parametric vector, then doing calculus over the parametric vector is more neat and clean, more intuitive and more informative. So this is what the idea is. But anyway, we have done it, and we have showed that what are the limitations from where we cannot go in the parameterization of calculus vector, like we took the case of paraboloid. So in case of paraboloid, z equal to x square plus y square, and if I calculate the vector field, then 2xi plus 2yj, there we felt that we cannot convert it to parameterized vector. Anyway, but if it was in 2D, then we could convert. So it came as ti plus 2tj. This is what we saw as for ti plus 2tj. So exact vector field to the parametric. I mean y equal to x square. That is the parabola. So it came as ti plus t square j. This is what we saw. So anyway, but everything in algebra is not possible to have the parametric vector. But whatever, the algebra is algebra, and it is the source of the calculus. So it is something like ab original in calculus, native in calculus. Okay, so algebra and then the gradient vector through the algebra. So we had gradient vector through parametric vector. Now we will have gradient vector through algebra. We also call it vector field. Anyway, now we will start with a kind of a parabola again, and then we'll go to paraboloid, then we'll go to circle, and then we'll go to sphere, and this is how it should be. So if I see the parabola equation, okay, so if I see the parabola equation, then this is typically a parabola. This is typically a parabola, and this is center. So if this is origin 0 comma 0 in 2D, then this is typically a parabola. Okay, if this is typically a parabola, then what will be the equation of parabola? So that is y equal to kx square. Let's say k equal to 1. So y equal to x square. If y equal to x square, then the dy by dx is 2x. If y equal to x square, then dy by dx equal to 2x. What is dy by dx? Dy by dx is, if I take this parabola, please concentrate. If I take this parabola, this is x-axis. This is x-axis. So, okay, if I take this parabola, then this is x-axis, horizontal x-axis, and this is y-axis. This is y-axis, and this is x-axis. If that is the case, then y equal to x square. If I keep changing the x, then y would be square of x. That is the equation of the line. If I say dy by dx equal to 2x, then dy by dx, rate of change of y per unit change in x. If x changes 1 unit, then how much y is changing? So if I say dy by dx equal to 2x, means if I change 1 unit along x, then it changes 2x, not 2. If there is 1 unit change along x, and if it is 2, then it is double of x. If there is a line that is called 2x, if this is x-axis, this is y-axis, then there is a line called 2x, then it is more than 45 degree. It is like this. Then dy by dx equal to 2. Per unit change in x, if I go, if this is the line, and there is 1 unit change along x-axis, it brings 2 unit change along y-axis. 1 unit change along x-axis, it brings 2 unit change along y, everywhere, constant. So that is dy by dx equal to 2. But here, dy by dx equal to 2x. If there is 1 unit change along x-axis, there is 2x unit change along y-axis. So along the y-axis, whatever change we are seeing as per 1 unit change. So if this is parabola, and this is center, if this is parabola, this is center. If we go along x-axis, per unit change in x-axis brings 2x. So what is x? At that time, the unit of y change depend upon. So if x is 0, then there is no change in y. Okay. If x is 2, then change in y at that point. Every point, the change in y is different. That is dy by dx equal to 2. If dy by dx equal to 2x. If x equal to 10 at that point. So if this is parabola, and we go along x and x is 10, at that moment, that moment, origin, if I move now and go in x direction where x is 10, at that moment, if I increment 1 unit can be 1 nanometer, 1 micrometer, 1 millimeter, depends upon the user. How how fine, how intricate he wants the value. At x equal to 10, if I vary 1 unit, then the variation in y is 20. At 10, the value of y is not 20. At 10, x equal to 10, If I vary 1 unit along x-axis, the equation, then along the y-axis it would vary 20, 2 into x. If x equal to 100 at that point, when x equal to 100 at that point, if I vary equation 1 unit along x-axis, then in y it will change 200. So dy by dx, the variation that is seen in y with 1 unit change in x, that depends upon the value of x. At each x, that variation that is seen, the rate of change of y per unit change in x is not constant. It is varying. Okay, that is dy by dx. So now let's see that our line equation is parabola. Line equation is parabola. So if x, the way x is growing, so if this is parabola, the way x is growing, y is growing very fast. So at one moment it will be like vertical one. So if so rate of change in y that we see, it also keep growing. So at any moment, if I see the rate of change in y, then rate of change that in y, any moment if I see, then that would keep changing. So that is 2x. So now what is the kind of equation of the line? So equation of the line is, we can consider the direction. What is the direction? So direction is like this. The whatever the parabola is, direction is like this. Okay. So direction of the line is like this. If that is true, then what is the direction? What is the dy by dx? So dy by dx is nothing but at each point what is the slope. So this is gradient. At this, if x is this, then y is this. So this is x comma y. If x is this, then y is this. That's why this is the point. At this point, dy by dx is gradient is tangent over here. So what is the equation of the line that at a point that is x comma y, that is the dy through the dy by dx, that is the tangent. Or if I say now at any point I want the tangent, if this is the parabola, if this is the parabola, then at any point I have different tangent. Can we see? If this is the parabola, here tangent is vertical. Where tangent, if I draw slowly, it is going becoming horizontal. So that is the tangent. So if dy by dx is the dy by dx, if I know the equation of line is nothing but y equal to mx, that is dy by dx. So when x is 10, every point the tangent line equation is different. If x is 10, at that time dy by dx is 20. In that case, at that moment, the equation of the slope is y equal to 20x. Okay, so the equation, okay, at that moment is y equal to 20x. When x equal to 2, the equation of tangential line is y equal to 4x. So tangential line, it goes like this. This is gradient, not the gradient vector. I'm talking about gradient line. So at any point, if this is the vector, this is the parabola, then at any point, what is the equation of the gradient line? So gradient will be vertical like, and then slowly it will be tangential. Okay, this is the equation of gradient line y equal to mx, where m is dy by dx. What is gradient vector? Gradient vector, now the vector that is kind of, it shows, it gives us a hint about the variation. Okay, now if I have equation y equal to x square, then I can say it is, or y equal to x square plus c is constant where it intercepts. So if I kind of, this is origin, if I move it up c, then y equal to x square plus c, or y minus c equal to x square, y equal to x square plus c. So The equation of the line, we can now see that that is y square x square minus y equal to minus. If I take a derivative, their gradient comes. So if I take derivative along x-axis, what is the change I see, and along y-axis, what is the change I see. Okay, if I take derivative or the kind of a partial derivative, then along x-axis, now 2x square minus y equal to minus c. If that is the formula, or x square minus y, more or less I can say x square minus y. Now if I differentiate this line with respect to x, it will come as 2x. Whereas if I differentiate it with respect to y, okay, if I differentiate with respect to y, then it will come as minus 1. So now we call it that if I differentiate something along x-axis, means how much we see the change when we go along the x-axis. So we can say that that is 2x. So it, and along y-axis, if I differentiate, then it will come as minus 1. So 2xi minus 1j, that is the gradient value. 2xi minus j, 2x square minus y square. If this is the function, then 2xi minus j. If I differentiate along x-axis keeping y as constant, then it will become 2x. If I differentiate along y-axis keeping x as constant, then it will become minus 1. So 2xi minus j, this is the gradient vector. Okay. Now you remember that in parametric vector things were different. If it was ti plus t square j, the gradient vector was I plus 2tj. I plus 2tj. Now here x square minus y is there, then it is 2xi minus j. So whatever we received through the parametric vector, what we are receiving now, they are perpendicular to each other, or what? Now, if this is the kind of equation of a parabola, if this is the equation of a parabola, then if I see the gradient vector that we have calculated 2xi, 2xi minus 1j, 2xi minus j, then at each point j component, the y component is minus. So minus is vertically down. If this is y axis, this is x axis, then minus is vertically down and x is in this direction. So as we go along, then x portion would keep increasing where y portion is minus 1. So the component along x axis would keep increasing if we go along the x axis. So the gradient vector is 2xi minus j, 2xi minus j, 2xi minus j. Then if I keep increasing x, if I go along the x-axis, then as we go along, the x component of the gradient vector would keep increasing. It will become more powerful. Whereas the minus y component will be 1 over. So if we see again, if this is parabola, if I want to calculate the gradient vector here, okay, so if this is parabola and if I want to calculate the gradient vector here, as we go along x-axis, then x component is becoming more powerful. X component is becoming x component is becoming more powerful. So beginning, it will be at the beginning, when x is less, it will be something like tilted. But as we go along, the x component become more powerful in the vector. So it looks like the vector, what gradient vector we are talking about, this, if this is the case, the way it is going, it is becoming perpendicular to the line. Okay, so if I see 2xi minus j is a gradient vector, if x is 1, then it is 2i minus j. If that is the case, if x is 1, if this is the origin and this is x, then it will be like this. That is again perpendicular to the surface. Can you see? Now, if I go along, then x is growing and y is minus 1 only. So it is becoming horizontal to xx. Slowly, if I go more in x, then it will become more or less parallel to the x-axis. If that is the case, then looks like the way we go more in the x direction, the the curve becoming vertical, 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 vertical. If that is the case, then gradient vector is becoming horizontal, horizontal, horizontal. This proves that if it becomes exact vertical, more or less, then at that time the gradient vector is exact horizontal. So it is perpendicular to the surface. So whatever surface we are saying, whatever the line we are saying, then the line from the line, so if this is parabolic line, this is parabolic line, then the 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 gradient vector is like it's perpendicular to it. So it will be like perpendicular to this. So if a parabolic line is like this, then gradient vector will be like this. Okay, so this is kind of a story of the calculating from the algebraic equation the gradient vector. Now suppose this is paraboloid. If this is paraboloid, then x square z equal to x square plus y square. Earlier y was x square. Now z equal to x square plus y square. If that is the case, then it is x square plus y square minus z is the equation. Z, if I take that side, then 2xi plus 2yj minus zk is the gradient vector. X square plus y square minus z, if I differentiate with x, then it is 2xi, 2yj and minus k. Now, what it tells the paraboloid. So, if I have a paraboloid and if we are calculating the kind of gradient vector, then what would be the condition of paraboloid? So, what paraboloid I can take into the consideration? Okay, I don't have much in paraboloid. Can we consider kind of this as paraboloid or this as paraboloid? Okay, so I believe this is better. So now if this is paraboloid in the sense that down, it will be parabolic in all the directions. So earlier we had parabolic only in xy direction. If this is z, if this axis is z, this is x and this is y. So this is xy plane. If this is xy plane, then this is x axis, this is y axis, and this is z axis. If that is the case, in xz plane, we have a parabola. In yz plane, we have a parabola. Yz plane parabola, xz plane parabola. If I just rotate it, then it becomes a paraboloid. Okay, if I rotate it, then it will become like a paraboloid every direction. If this is the equation of paraboloid, then what will be gradient vector at any point here, at any point? So any point is x, y, z. So that is 2xi plus 2yj minus k, x square plus y square. Z equal to x square plus y square is the equation of paraboloid. If that is the case, then 2x square plus y square minus z is the equation that we have come through as far as calculating the gradient vector. So 2xi plus 2yj minus k is the equation of the gradient vector. If that is the case, then at any point, now if I see any point, then 2x. If I go along x-axis, if now we are talking about, now if this is the paraboloid, if this is the paraboloid, then if I go along, then how would be its gradient vector? If this is the paraboloid, then if I go along, what would be its gradient vector? That is the question. Now, if we go along x-axis, then 2xi. The whatever the gradient vector, can we see this gradient vector? This gradient vector has three components: one along x-axis, one along y-axis, and one along z-axis. That is the vector is. It has three components. If it is three dimensional. So if we are going, if I am shifting the x, y, z, then if x is growing, then gradient vector x component will grow as 2x, y component will grow as 2y, whereas z component is constant minus 1. So if this is vertical is z, then minus 1 means it will be tilted like this, down. And then this is along the z axis. Okay, this is z axis. So what, how far it is tilted, that is x, z axis. How far it is in horizontal side, that is x axis. How far it is in vertical side, that is z axis. How far in this side, that is y axis. So any point if I calculate, if x is 10, then 20i plus 20j minus k. So at any point, if y is 0, I am calculating in xz plane, 20i minus j. So if that is the case, if this point is 20, if point is 10, x equal to 10, and z equal to x equal to 10, and z equal to anywhere x equal to 10, if this is x axis, x equal to 10, and z along x equal to 10, any point we are taking which is touching the paraboloid. So if x equal to 10, then wherever it is touching the paraboloid. So if this is paraboloid and this is x equal to 10, wherever it is touching the paraboloid. If it is touching the paraboloid here, then whatever z is. But at that moment, if I try to see the gradient vector direction, then it is 10 into 2, 20i minus j. So 20i minus j means vertical minus vertical component, minus j. Vertical component is very less and horizontal component is high. It is like parallel to x-axis, little bit it will be down. So it will, the gradient vector would swing in xz plane, where it will be parallel to x little and slightly down, because z-axis is minus 1. If x is 1, then it is 2i minus j. So if it is x is 1, then it is like this. As we go along, it is becoming flatter, flatter, flatter. So that is, if I have a paraboloid, so xz plane same as what we saw in yx in two dimensional. So if this is xz plane, it is same as the vector would be like this, and slowly it becomes parallel to the x-axis, slightly down, minus 1. But as we go along x, as we go along the x, then the strength of x-axis would keep increasing, and it is 2xi, variation function over x. Now, if I see the yz plane, again it is 2yj minus k. So, if I see yz plane, at the beginning it will be down, but if I go along, then it will be flat. Then it will be down like this. So, that is, if I take y as 0.000001, then again the y component is negligible, but z component is always minus 1. So if this is paraboloid, if this is paraboloid, and if I go in yz plane, at the beginning where I am at center, it is completely down. So it is perpendicular to the parabolic equation. So it is completely down. But as we go along, slowly it will become flatter, 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 because y component is growing with the y increase, where z is always minus 1. So if I have a paraboloid, and at any point x comma y comma z, where it meets the paraboloid, there it is 2xi plus 2yj minus k. So it is perpendicular to the surface. So if this is paraboloid, then here, if this is the surface, then here it is exactly perpendicular to the surface. If this is the surface, then exactly perpendicular to the surface. If this is the surface, then exactly perpendicular to the surface. So, so if x is 10 and y is 2, okay, irrespective of z, then it is 20i minus 4j minus k. So there, along x-axis, the direction will be flatter, whereas along y-axis, it won't be exactly along y. It will be direction of x1 a little bit down. So it will be like this. If you keep going along y-axis, keeping x as 0, then it will be along the y-axis little bit down. If I keep going along x-axis, keeping y 0, then it will be along the x-axis little bit down. More we go right along x-axis, it will be flatter, flatter, flatter. More we come to origin, it will be in direction of z. So at origin, it will be like this. Whereas the paraboloid is like this, then at origin, it will be like this, and then slowly it will become flatter. If I take YZ plane, again it will be like this, and slowly it will become flatter. So at any XYZ now we can imagine. So if this is 3D, if it is 3D, this is x-axis, this is y-axis, this is z-axis. Then if I take like this, then it will be, if surface, the paraboloid surface is going like this, it is going like this, then the gradient vector, first it will be down and slowly it will go like this. So that is the story. We'll move on with the sphere, and then we will see how it makes sense when we see kind of parametric vector and calculus and algebraic calculus, parametric vector calculus and algebraic calculus. There we see 90-degree difference, orthogonal difference between the gradient vector that we are calculating, but it doesn't make much difference as far as what is the surface equation we are doing. So surface equation with the surface here, algebra story is about points. If I take paraboloid, then at each xy I have a z value. So each xyz point I take. Whereas if I go to parametric vector, at each point we have vectors. So if we have vectors, then the gradient vector will be different. Whereas we have points. So parabola, the points are in parabolic shape. The points are in parabolic shape, then gradient vector is perpendicular to the direction of the point, then certainly it will be like this. Whereas if I see the parametric vector, then vectors are in this direction. Okay, if vectors are in this direction, vector is this direction, then their gradient will be little bit different. More we'll see, it will become more clear when kind of we'll see the sphere example, and then we'll compare and we'll see that where what is useful more. So that is the scenario. So that we will see more in a kind of gradient vector in algebraic side. That will see.